Thank you for having me. My name is Sam. I'm here to talk about PowerBlade, which is our low profile, true power, plug-through energy meter. These numbers might be familiar to some in this community, but it's still kind of a stark reality, which is that residential and commercial buildings in the U.S. consumed almost 3 petawatt hours of energy in 2014. That's 1,000 watts in constant use, day and night, for every man, woman, and child in the U.S. That's kind of interesting in that those numbers actually aren't changing that much over time, but what is happening is that it's shifting away from the obvious loads, HVAC, your air conditioning and your heating, and it's shifting toward MELs, these miscellaneous electrical loads, your outlet loads like your blender and your television. Devices exist to help us understand these loads, power meters, some you might even be familiar with. But people don't use them. Some people are familiar with kilowatt, some people even have one or two, but they often don't use it as part of their daily lives, and nobody that I know of has instrumented their entire house with kilowatts or watts up. That would be so burdensome. What we really need is an unobtrusive power meter. Something that can be so small that it can actually sit between the plug and the outlet. You wouldn't even see it while it's in use. This now is small enough that when you unplug the load, the power meter travels with it, as opposed to staying with the outlet. What that does is it enables a new paradigm of plug-load metering, where the data and the device are inherently bound to the load being measured, and not the arbitrary outlet that it was plugged into. So with that in mind, we have designed PowerBlade, which is our 1 inch by 1 inch by 1/16 of an inch energy sensor. Arriving at this design is not simply doing what's been done before, but better. And the reason I say that is that there's 5 components that make up a power meter, 5 functions that each power meter must do. And for each one of those functions, the decisions made in existing meters are fundamentally tied to the form factor of those systems. Those 5 things are: convert the AC mains voltage to a usable DC voltage, measure voltage, measure current, calculate power and energy, and communicate those measurements to the user. For each one of these things, I'm going to go through why the existing implementations can't be scaled down, and I'm going to propose a new, smaller method. By combining 5 of those smaller methods, we can arrive at the design point of PowerBlade. So to start, converting the AC mains to a usable DC. In all the meters that we've evaluated, the circuit design itself varies somewhat, but the overall topology is the same. And that is that you convert from a high voltage AC, 120 volts AC, to some usable DC by shunting most of that power over this input Z-in. In all the devices that we've evaluated, Z-in is a capacitor. So when you actually break open 3 of the more popular meters that exist, the Belkin Insight, the Kilowatt, and the WattSub Pro, this input shunt Z-in is immediately recognizable because it's enormous. And it is the size that it is for 2 reasons. The first is that it's rated for the mains voltage, for that 120 volts that it'll experience. But the second is that it needs to store the energy required to power your load during each half cycle. And that's an important takeaway, which is that if you really want to scale down the size of your supply, you have to scale the load current that it's supplying. But something else that's kind of interesting there too is that Z-in does not have to be a capacitor. In fact, it could be a resistor. The operating mode at that point is a little bit different, and the requirements are different as well. Now it needs to be small enough to provide enough current, and it has to be rated for the power that it will dissipate. And that's the interesting point, and that's why the existing meters don't use resistors in place for that shunt, because at the power point that they operate at, say 10 to 100 milliamps in continuous operation, that resistor would burn 1 to 10 watts at all times, which is not only wasteful, it's just kind of silly. However, what we recognize is that if you scale your load from that microamps range, or sorry, from the milliamps range into a microamps range, so your device only draws 10 to 100 microamps, then the resistor is only dissipating a few hundred milliwatts, and that's actually pretty reasonable with standard package components. So that takes us to the design space for Z-in. And on this figure here, we've plotted 3 families of resistors and 3 families of capacitors. for both the volume that that component will occupy and the current that it could supply to the load. Right away, our system has some maximum volume, and we determined this experimentally just on some outlets in the United States, and that eliminates certain components. The next thing to recognize is that there's now two Pareto optimal curves here. There's one for current and volume, and another one for the capacitors that don't add an idle power. There's an idle power optimal curve. Our selection for our design is a 1210 package 80 kilo ohm resistor, which we intentionally selected somewhat back from the frontier to allow some tolerance in our design, and that yields us about 800 microamps that we can use in continuous operation. So the next function we have to do is to measure voltage. And although that can be done with reasonably standard techniques, the hard part is actually establishing contact with the AC. In every meter that we've evaluated, contact is done through an AC socket. So the load plugs into the meter, and the meter plugs into the wall. This inherently bounds the size of the meter by the size of that socket. And as you can see, the socket in this image is substantially larger than our entire system. So that's simply unavailable to us. Instead, we need a planar contact method, one that won't introduce any extra thickness over the PCB and the components themselves. And for that purpose, we evaluated some flexible tabs built into the PCB itself. So as the load passes through, the original plugs plug into the outlet, but we make contact so we can power ourselves and measure voltage. These rigid flex circuit boards are not designed for elasticity. So what we noticed was after several insertions, the tabs would bend and then not return to form and would no longer provide contact. So we evaluated several different layer stack-ups as well as tab lengths, and we reached a design that could give us about 20 insertions of good strong contact with those tabs. The next thing we need to do is measure current. And once again, if you look at these existing meters, there's a common theme, and that's a sense resistor. So you break one of the AC paths, put it through a resistor, and measure voltage to measure current. This is attractive because the resistor is small, affordable, and highly accurate, but it's only available to systems that can break the path. They're using an AC socket. Since, in our case, the original plugs pass right into the wall, we have no opportunity to break the path, and therefore can't use a sense resistor. However, we note that as current flows through the face of PowerBlade, it'll generate a magnetic field. And since current's flowing in opposite directions in either plug, those fields will add constructively between those plugs. One methodology for measuring that field and then working your way back to current would be a Hall effect sensor. And really the problem here ends up being just the physical characteristics of Hall effect sensors themselves, but it would need to be in the plane of the plug rather than the plane of the board. And you could potentially work around that, but what we also note is that a horizontally wire-wound inductor, standard component, placed in that field can act as a search coil, which is a type of magnetic sensor. And this is a very attractive option for us because it's very small, inexpensive, and inherently low power. But there is one drawback, which is that the output of a search coil isn't actually related to the current, but instead it's related to the derivative of current. So for a load like this, for a resistive load, a power factor of 1, the voltage and current should be fully in phase with one another. The output of the search coil, however, will be the derivative, and it'll just need to be integrated before it can actually be used to calculate power. Final thing to note about this inductor is its placement, and that is really due to the rapid fall off of that magnetic field strength. The ideal location for the inductor is as close to either prong as possible. When we place it close to the neutral prong, the wider of the two, because our ground is referenced to neutral, so there's no spark gap considerations, and we can really put it as close as we can physically achieve. Finally, the meter needs to calculate power and energy. And once again, going back to the state of the art, we see a common theme, and that's an energy metering IC, something that takes voltage and current as inputs and outputs power readings over a serial interface to a microprocessor. And actually, in both the Belkin Insight and the WhatsUp Pro, they use the same chip, the ADE7753. It might be familiar to some in this community. In PowerBlade, though, that ADE chip requires resources that we simply do not have. And the first is, if you look at the profile of this chip, 71 thousandths of an inch, that's wider than our entire system. we're only about a 16th of an inch. The other thing to note is that on the ADE requires 25 milliwatts to operate, which is more than 3 times our entire power draw. So that's simply unavailable. What we do instead is we implement our metering algorithm as custom software on an MSP430. This allows us to reduce the chip count in our system, which on a 1 inch by 1 inch PCB is one of the most important metrics of the design. Specifically, we use the FR5738. Now, we selected that because it's extremely low power, about 80 microamps per megahertz, and includes 16 kilobytes of FRAM. Non-volatile storage like FRAM is important in power meters because that cumulative energy number, watt hours that we're all familiar with, really shouldn't reset if your house loses power if the load is unplugged. I also want to note here that at this time the MSP430 is doing the integration to convert from that surge coil current back to the actual signal. The final thing that the meter needs to do is to communicate those measurements to the user. And when we look at the existing meters, there's a really common theme here, and that is either a visual readout, like a screen, a wired interface, like USB, or a wireless radio, Wi-Fi, Zigbee, whatever. When you think about where PowerBlade exists, a screen and even a wired interface are kind of invalid options. You wouldn't be able to see the screen since it's behind the plug. And that leaves us with a wireless transmission. And what we note here is a wireless transmission requires a certain fixed amount of energy, a certain energy quanta, if you will. And based on our selection of our power supply, or Z-in, if you will, we can evaluate several different radios for, based on their energy quanta, what their maximum wake-up rate will be based on our available power. We ended up selecting a BLE radio, the NRF 51822. And we selected that both because we could achieve, on the order of about 10 to 100 packets per second in the maximum, but also because the BLE interface is very attractive to us, that you don't need any infrastructure. It can connect right to your smartphone or tablet or whatever. So that takes us to PowerBlade functioning as an entire system. In steady state operation, the MSP430 measures voltage and current at 2.52 kilohertz. We selected that frequency as both an even multiple of the 60 hertz being sampled and an even divisor of the sampling clock that we're using of 32 kilohertz. The MSP430 does the calculations and transmits measurements to the BLE radio once per second, and the BLE radio actually transmits those measurements in advertisement packets at 5 hertz. That does result in 5 identical packets per unique measurement, and for us that just means that it increases the likelihood that one of those packets will be received. In each packet we transmit true power, apparent power, and this cumulative watt hours number, the total energy measured. So, does it actually work? We evaluate PowerBlade for its accuracy and true power. And we do this in 2 steps. The first is a benchtop test, where we use a programmable AC load set to a unity power factor. For this test, on the range from 2 watts to the load's maximum of 1200 watts, the average error is 1.13%. So we're highly accurate in this very controlled case. But what we really care about is how well does PowerBlade perform in the real world on loads that it'll actually be measuring. So this is a cross-section of loads from our lab and from our apartments, and this list here is sorted by power factor. A few call-outs. The highest powered loads we measured were a toaster, a vacuum, and a microwave. And the microwave is all the way up at 1800 watts. And although our absolute error here is somewhat high, 15 to 20 watts, the percent error is quite low. The lowest power load that we measure is our wireless router, and although the percent error is a little bit higher here, the absolute error is quite low. However, for low power factor devices, and in particular for the blender and the drill, whose current waveforms are just highly distorted, our error does spike significantly, all the way up to the 30 to 40% error range. And to think about why this is the case, we need to go back to the current waveforms. So if you can think about what's actually shown here is the actual current as well as the measured current, which is the internal signal in the MSP430 post-integration. We're also showing here the absolute error to kind of get a sense of how well we're doing. What you can see is on the resistive load, where the current waveform is a gradually varying signal, our software integrator can fairly faithfully reproduce the underlying current. However, for the blender, it has significant higher frequency components in that current waveform. Our integrator suppresses those and our error spikes. This is really one of our primary areas for future development as we continue to work on this system. We also evaluate PowerBlade on some micro benchmarks that really just affect the usability of the system. The first among these is cost, and that is that the component cost in PowerBlade is low, about $11 per unit. Our target for this design, once we've had a chance to optimize for cost, is about $5 per unit. We would like to do deployments of about 20 units for $100 per deployment. The second thing that we wanted to pay attention to was, does this form factor, does sitting between the wall like this compromise the wireless performance? We evaluated this in a 3-step experiment. We placed a receiver in the same room as PowerBlade, in an adjacent room, and 20 meters away. Nominally, we should be receiving 1 unique packet per second, that's the rate that the MSP430 is actually transmitting. What we find is that in the same room and the adjacent room, we're basically receiving every single unique packet, which really just means that at least one of those 5 redundant packets is being received. And by the time you get to be 20 meters away, we are losing about 20% even of the unique measurements. But I want to point out here that since each packet contains that cumulative energy, that watt-hours number, overall accuracy is maintained. What you do lose is the resolution of that one packet, but any packet that you receive after that will have the correct watt-hours number. The final micro benchmark, although perhaps the most important, is safety. And that is, our supply is non-isolated. And so our entire circuit is referenced to the neutral plug, which can be a safety concern. There's also areas on the board that are connected directly to the phase or hot plug, which can be quite dangerous. For our own protection, we have already evaluated using epoxy overmolding. Basically, we paint it on, and it protects the user from accidental shock. In the future, we're going to move toward a more injection molded style overmolding. It's a little bit easier to manufacture. Going forward, there are really 2 things we want to focus our development on. And the first is accuracy. So as I already discussed, the software integrator that we use performs well on some devices and really poorly on others. This is actually also manifest in an error in power factor or in apparent power. We believe that by implementing the integrator actually in hardware as opposed to in software would help this. And we also recognize that we need to continue to improve our custom metering algorithms. The other thing that we want to move away from is those flexible tabs. So I mentioned that we got about 20 insertions in our current design. And that actually might be a valid number given that the meter should stay with the load. We really wanted something that will have a little bit more longevity. So to that end, we mount some spring-loaded pogo pins in the plane of the PCB, such that as the load passes through, these pins provide contact. Since the pins themselves are designed for lots of insertions or lots of compressions, we're finding this to be a much more long-term solution. We actually have not yet found the ceiling, if you will, for how many maximum insertions these pins can give us. Finally, we're kind of at a point now where we'd like to make a bunch of these and start doing some deployments. In conclusion, PowerBlade is the smallest, lowest power wireless true power meter that we are aware of. What that size enables is this new paradigm in plug-load metering, where the data is bound to the load. The other thing to note is that our supply miniaturization, this relationship between if you want to scale the supply, you have to scale the load, that can be applied to other systems that are trying to be miniaturized. And finally, we've established the viability of this form factor for future projects. So you can imagine taking our circuit board and our power supply, ripping out the front end and putting in your own, and you have a permanently powered, unobtrusive sensor that doesn't block any outlets from use. We're giving a demo tonight, so please come see our demo, and I'd love to take your questions.